So welcome you to this module. So last module we introduced the concept of unbiased tests. And such a need arose because we realized that uniformly most powerful alpha tests may not exist in many situations, especially when you have a nuisance parameter or your hypothesis is two-sided hypothesis, like theta is equal to theta naught against theta naught equal to theta naught. So then what we did is we restricted our class of tests under consideration by imposing the condition that the power should always be greater than or equal to the level of significance. And we called any such test to be unbiased. So we restricted ourselves to be the class of all unbiased tests. Note that by enforcing the condition that your test should be unbiased, I have gotten rid of the tests which were not using data at all, like phi x equal to 1 or phi x equal to 0. Because for phi x equal to 1, one kind of probability of type 1 error is 1, whereas probability of type 2 error is 0. For phi x equal to 0, probability of type 1 error is 1 and probability of type 2 error is 0. Sorry, other way. Phi x equal to 0 test, expected value of phi x is always 0, so that means probability of rejecting h naught is always 0. So whether probability of rejecting h naught, whether h naught is true or whether h1 is true, it is always 0. But these tests, for these tests, first of all, level of significance you cannot achieve to be alpha. Even if you, so by imposing unbiasedness, we have gotten rid of a lot of undesirable test functions. So then we said that let us try to find out the best unbiased test. So that means the unbiased test for which the probability of type 2 error is minimum. And that we can do using the following result, which is quite general in the nature. Of course, it mainly holds for exponential family. So what you have is you have a phi, which is f theta. Theta is a single parameter, but then you have a set of nuisance parameters which are phi. Phi could be a vector. Theta and phi vector belongs to capital theta, where theta is a vector of rk plus 1. That means theta is a real valued and phi is an element in k-dimensional Euclidean space. So theta is real valued. Phi belongs to rk. And theta contains a k-dimensional rectangle. It should be k plus 1 dimensional rectangle. In other words, we say that it is a full rank. That means all these parameters are linearly independent. There is no linear relationship between them. And what I assume is your f theta phi x is of the type c theta phi e to power theta tx plus summation I is equal to 1 to k phi I ux. Note that there may not be any phi, right? So k can be anything from 0 also. So k you can take to be 0. K is equal to 0 means phi belongs to R0. R0 means empty set. That means there is no phi, basically, I am saying. So this covers one parameter exponential family also. And what I assume is this u1, u2, uk constitute the vector ux is same as u1x, ukx. So first case we consider is h naught, let theta naught r be fixed. And I consider the situation where I am interested in testing h naught theta less than or equal to theta naught against theta greater than theta naught. And of course, you can interchange it because any hypothesis about theta less than or equal to theta naught can be converted into theta greater than or equal to theta naught by considering here theta, converting theta into minus theta, and Tx becomes minus Tx. So suppose you have to test this. Of course, you know that if there was only one parameter, there were no nuisance parameter over here, UMP alpha test exists in such a situation if your family of PDFs has a MLR. So in this case, even if when you have a nuisance parameter, there exists UMP alpha, UMP U alpha test, even when nuisance parameters are there, given by. So the nature of test is exactly the same, which is 1 if Tx is greater than C times Ux. Now this constant depends on this vector Ux. So if there were no U's, it would be only C. So it is more general than the one result which we did earlier. This is gamma of Ux if Tx is equal to C times Ux. And this is 0 if Tx is less than C times Ux. Where C of U dot and gamma of U dot are such that E theta 0 of phi x given U is equal to U is same as alpha for every U. All right? So this conditional PDF is same as alpha. So of course, this ensures that x to phi x given U should not depend on theta. No, theta naught, so anyway, it will, there is not an issue. But ensuring that level is alpha, you will have to show that E theta less than or equal to theta naught, phi of U is alpha. So that one can prove easily that such a test which utilizes the maximum flexibility given to it is the UMP alpha test. Second situation could be, let theta 1, theta 2 line to R be fixed and theta 1 is less than theta 2. What I do is I consider testing H naught theta less than or equal to theta 1 or theta greater than or equal to theta 2 against theta lies between theta 1 and theta 2. Now note that in the case of exponential family, of course, in the case of MLR, we could not prove that a general result which guarantees the existence of UMP alpha test. But in the case of exponential families, what we had seen is, in such a situation, UMP alpha test exists. What I'm pressing over here is that even if you have a nuisance parameter, UMP alpha test exists, and tests would be exactly of the same type as was in the exponential case, except that C may depend on Ux. So your phi x is nothing but 1 if Tx lies between C1 of Ux less than C2 of Ux, gamma I of Ux if Tx is equal to Ci of Ux, I is equal to 1, 2, 0, otherwise. Of course, how do you choose this C1 Ux, C2 Ux, and gamma Ux? Such that expected value of phi x given Ux equal to U or U is equal to U is same as alpha at the point theta 1 as well as theta 2. So where C1 U, C2 U, gamma 1 U and gamma to u are such that expected value of under theta I of phi x, given that u is equal to u, is same as, sorry, e theta 1 phi x is same as e theta, yeah, so you can write down e theta I phi x is same as alpha for every u. So in these cases, so these part A and part B are much more general than the result which we did before, because if you take k is equal to 0, that means there are no u's present, they give the result which we already discussed before. Now comes the situation where UMP alpha test does not exist even in the exponential family. So one such situation was you interchange here h0 and h1. That means h0 becomes theta between theta 1 to theta 2, and h1 becomes that theta is in the extreme. Now in such situations we are not able to find UMP alpha test even in the one parameter family. At least we were not able to find a general result for the one parameter family. Now in this case we can prove that UMP alpha test would exist. So this is what the result says. So let theta 1, theta 2 belongs to R. Theta 1 is less than theta 2. What you're interested in testing is h0 that theta 1 less than equal to theta 2 against that theta is less than theta 1 or theta greater than theta 2. UMP, so there exists a UMP U alpha test given by exactly which would be same as 1 minus phi x. So let me write down this would be 1. Of course here MLRs everything is there. That means you reject for when theta is in the extreme. So that means t is in the extreme if there is MLR property, which is happening over here. T is in extreme, that means if Tx is less than C1 times Ux, or Tx is greater than C2 times Ux, and you reject it with probability gamma I of Uix, if Tx is same as Ci times Uix, 0. Otherwise, where how do you choose C1 and C2? Where C1 U, C2 U, gamma 1 U, and gamma 2 U are such that same condition holds, right? Such that E theta 1 phi x given u is equal to u is same as E theta 2 phi x given u is equal to u. So when I am writing down given u is equal to u, that means given ux equal to u is same as alpha for x. So we see that UMP alpha test exists. Now the remaining case is when I have to test theta is equal to theta naught against theta not equal to theta naught. Even in such situations, UMPU alpha test exists, at least in the exponential families having nuisance parameters. So this is the last part. So let theta naught be a fixed real number. What you need to consider is theta is equal to theta naught against theta not equal to theta naught. So there exists a UMPU alpha test given by. So again over here, when theta is restricted to theta naught, if theta is theta naught away from theta naught in either direction, you would reject h naught. So that means you would reject h naught if phi x is 1, if Tx is less than C1 times Ux, or Tx is greater than C2 times Ux. Gamma I Ux if Tix is same as Ci times Uix, 0 otherwise. So how do you choose this? So let me write down just over here, where C1u, C2u, Γ1u, and Γ2u are chosen, such that at theta naught, phi x given u is equal to u is same as alpha for every u. So again, I would like to emphasize here, when I say phi x given u is equal to u, it means phi x given ux equal to small u is a vector. And E theta naught phi x Tx given u is equal to u is same as alpha times E theta naught Tx given u is equal to u for every u. So there are these two conditions which need to be satisfied. So this tells you that in one parameter exponential family, in many situations UMP alpha test exists, especially if UMP alpha test does not exist. Now in truncation families, you can easily see that even in the case of truncation families like uniform 0 theta or exponential with location parameter e to power minus x minus theta, you can find uniformly most powerful test for theta is equal to theta naught against theta not equal to theta naught. That may not be the case for the normal family. So in such situation, you have to find the UMP U alpha test, and UMP U alpha test is given by this phi x. So now, as we saw that in the estimation problem, sometimes your estimation problem or a testing problem might have a nice structure. Then, if it has a nice structure, you would expect that that nice structure gets passed on to the kind of tests you would be considering. So the invariance principle then would suggest that I should consider only those tests which are invariant tests. So that reduces the class of tests under consideration. And then there is a possibility that I may be able to find the best test within this restricted class. So that is what we'll start doing from the next module. Whatever I did in the last 4 modules, that was a review of basic concepts of testing of hypothesis, especially dealing with uniformly most powerful test and uniformly most powerful unbiased test. So now we'll start the content of this course, which would be dealing with invariant tests. So that will start from the next module. That's all for today, and thank you very much.